All right, welcome back to the final review. Let's talk about newer stuff now. All right, so I guess the first thing I want to talk about is searching. So searching is very important. It'll become even more important when you take CSCI 41. Searching algorithms are just about looking for something inside of something else. So in the context of this class, we've talked about searching for stuff inside of vectors or arrays. Like we've got something that we really care about finding. We want to know if it's there or not. So here, let's say we've got an array, and let's pretend that we have no control over what's in that array. We just know we've got a bunch of stuff, add a bunch of indices, and maybe we want to search for something like the number 3. So the goal of a searching algorithm is like to look through the thing and find if it's there or not. All right. So if you have a jumbled array, you have no clue about the order, you're kind of forced to but search through everything. All right, because you're not sure if the 3 is at the beginning or the end or somewhere in the middle. So that's the linear search algorithm. That's where you go through that whole array or vector from left to right, and if you find the thing you're looking for, like the 3, you give back the index where you found it. So that's your answer. That's what linear search returns. That's the index where it finds what it's looking for. If you're looking for something that is not there, like you go through, look for 42, you find nowhere 42, it does not appear, then you return -1 as the index where you found it, because that's an invalid index. All right? And yeah, linear search is always going to work out, no matter the array, because it's going to go and search through every place. It'll find the first one, all right? No matter if the vector is jumbled or not, or the array. All right, so let's see that. Or I guess, honestly, I trust that you can code that one. I'll code up binary search, all right? So binary search is the next one. That one, if you know that your array is sorted, you can take advantage of that and have a much faster sorting algorithm. So binary search is when you know that your array is sorted, because that gives you some very strong guarantees about where things may appear. So what would be the sorted version of that array? 0, 3, 5, 6, 7, 8, 9, right? So let's say that we're searching for, I don't know, 5 or something. With binary search, it's all about, all right, you can just look in the middle, play the guessing game. Like look in the middle first, compare 6 to 5, and do you see how you can, or sorry, let's say that's 8. That's a better example. So here we go. We look in the middle. That's the one thing we've seen so far. We compare the 6 to the 8, and we notice that, all right, it's bigger, so if it's anywhere, it's to the right. You can just cut off over half of your array. Does that make sense? Because the array is sorted, you can look in the middle, and you know that everything to the left of you is smaller, everything to the right is bigger. Isn't that nice? So you can just start in the middle of your search space. Originally, your search space is the whole vector or array. And then you can cut things off. It's like, all right, now your search space is between 7, 8, and 9, these indices. And then you search in the middle of that, and you find the thing. Do you see how you only needed 2 things? You only needed 2 checks, and you found something way over here. That's the beauty of binary search. It's much, much faster than linear search. It's logarithmic time versus linear time. Much, much better. All right? So you cut off potentially over half of the array each time, or vector, each time you search for something. And again, if you search for something that's not there, you want to give back -1. You want to notice that your search space has become empty. So you'll keep playing this actual same game if you're searching for 42, because it's big. So you'll, like 6, all right, it's somewhere to the right over here. You look at 8, it's like, all right, somewhere to the right, somewhere over here. And then you'll notice, all right, it's even bigger than 9, so it's like somewhere even bigger than 9. And so you'll like swap your low index, and it'll pass the high index, which won't make any sense. And that's how you know that you're done. All right, so let's have binary search as an example in code, and let me just show you how we're going to program it again. All right, so let's draw some pictures. So binary search, let's say that we've got this array or this vector, and I might as well draw it twice, because I'm going to need it a couple times. So 2, 4, 6, 8, 10, at indices 0, 1, 2, 3, and 4. And I'm going to want this drawing on the next slide as well, so here, just paste it. All right, so let's say that we're searching for the number 2 in this array. So the way that we do it, so like the value we want to search for is the number 2. Okay, the very first thing you do is you set up your search space. The lowest index where it may appear is index 0. The highest index where it may appear is index 4, because we haven't looked anywhere yet. And then you say, you calculate the midpoint of that. your mid index is going to be 4 plus 0 over 2, so 2. That's your mid index, and so you compare then the 6 to the 2, and you're like, all right, I see something smaller. I'm going to compare the 6 versus the 2. 2's smaller, so I need to look to the left of the 6. I know if it's anywhere, it's nowhere over here. You can cut off over half of the array. Does that make sense? So what that means is if you see something in the middle and you're something smaller, if you see something a little too big, you need to move your high index. It needs to go over here. That's now the new upper place where it could possibly be. It's 1 minus mid. Does that make sense? That's what needs to happen. So you're searching for 2. Your low index is still here, but your high index is now mid minus 1. This is the new upper limit of where it could possibly be. So see that? So if you're looking for something smaller than the midpoint, you got to change your high index. The opposite is true for when you see something bigger. So all right, here's low and high, and the midpoint of this, you're going to have to do division, integer division. 0 plus 1 over 2, and so the midpoint of that is going to be index 0. And so here's your new mid for the next round for your current search space. You'll be looking at the 2, and what do you know? You found it. Nice. This is maybe slightly more inefficient because it was already at the left side, but you could have been looking for the 10, and you still would have found it in like 2 goes. It's beautiful. So you found it. You return the index. All right. Let's say though that we were looking for something that wasn't there. Let's say that our value was really, I'll use green, was really 1. We'd still get to this point. Like we're still looking for small stuff. The midpoint is still index 0. Now we compare 2 to the 1 that we're looking for, and it's again something smaller. Right? And we know what to do when we see something smaller. It's the high index that needs to change, right? Just like this. So that means the low stays as it is, and the high index will change to be index -1. Or sorry, yeah, it will be index -1 because it's always going to be mid minus 1. Does that make sense? So now high is over here, and low is index 0. It's high is past low. Low is past high. However you want to think about it. That's how you know that your search space is empty. Like you're never going to find it now. It's over. All hope is lost. All right, so that's the example. So that's binary searching. So when you see something smaller, you change your high. Or when you see if you see something bigger than what you're expecting, you change your high index because you're looking for smaller stuff. And then if you ever see something bigger than what you're expecting to see, you're going to change your low index. All right, so that's the game. Let's program that. All right, so here's how I want to call it. Let's do it on vectors. 2, 4, 6, 8, 10. And yeah, I want to be able to do this, like binary search the vector v for the number 2, for the number 1. Binary search your vector v, and let's have it be constant reference because we want space savings and we also don't want to mess with the values. We just want to use them. And then we got the value that we're looking for. All right, there it goes. So yeah, let's do it. So initially, our search space is going to be the whole darn vector. So the low is 0, the high is size -1. That's our search space, where it could possibly be. All right. So there's those. And yeah, just like while the search space is valid, so while low has not passed high, it can be equal, can't be past it though, then we're good. So while we have a valid search space, we want to look in the middle of it. Calculate the mid index, go there, compare. Int mid index is low plus high over 2, and then now compare. If the thing I'm looking for is smaller than the thing I see at the midpoint, so it's like I am looking for 2 but I see 6, that means we change our high to be mid -1. That's the new upper limit. We were looking too far to the right, so that means look to the left. And that means change our high. High equals mid -1, because we just looked at mid, it wasn't there. So, all right, otherwise, what if the flip is true? if it's bigger, if the thing I'm looking for is bigger than the thing I see at the middle, so that's this example, it's like, all right, oops. I'm looking for 8, but I see 6, so that means my low index was too small. Like this should be my new low index, mid plus 1. Let's look to the right. We're looking too far to the left. Go to the right more. All right, so there's that one. And then otherwise, if it wasn't too big, it wasn't too small, we found it. So that's where it was. So we found it, and the index where it was this at mid, right? Mid was the index, so that's what we return. Return mid. And we keep playing this game as long as we have a valid search space. So while the search space is valid, we keep changing it as we're going inside this loop. But eventually, potentially, we might not find it. We might like be looking for something that's not actually there. So low will pass high, and like it makes no sense to look from between low and high where low is bigger than high. That's invalid. So if we ever get down here out of this loop, then we got to say return -1. That means we didn't find it. All right, so sad face. Now it's going to be binary search. And yeah, I think that's all the relevant code. Let us run it on these things. So yeah, index 0 is where the 2 is, index -1, nowhere is where the 1 lives. All right, so yeah, that's a good one to study. Can't forget it. And yeah, I think that's all that I wanted to say for that. What next? Let's talk about recursion. So recursion is fun. I love recursion, but it does take a while to sink in. So let's do some examples. So remember that recursion is when you have a problem and you're solving it in terms of smaller versions of itself. You're making functions, and so you're going to have your function call yourself. That's really nice. So in general, here's what you do when you have a recursive problem. Somebody wants you to calculate the factorial or something. Try out some examples and try to find a smaller version of this original problem inside of it. All right, so there's like the next smaller one, P of 4. You're looking for the next smaller one usually. You find it inside of itself, and then you generalize that example. You try a bunch of examples, see how it generalizes. Like, all right, in general, the factorial of n is equal to n times n minus 1 factorial. You figure that out. All right, that's your recursive case now. And then, like, keep on unwinding that, see when it stops making sense, or until like you have enough information you can immediately give an answer back. That's called a base case. Like, all right, everybody asks for factorial of 1. The answer is just 1. I'm done. All right. There might be a couple base cases, but sometimes there's just, a lot of the time there's just 1. Then you keep on iterating on that until you get it right. That's recursion in a nutshell. You find the problem inside of itself. All right. So let's do a power computation as an example. So we've done this before, but might as well do it again. It's like taking something to the 5th power. That's a recursive problem, because what is that but x times x times x times x times x? And there's a couple places. Where's the next smaller version of the problem, right? There's x to the 4th power, there's x to the 4th power, it's everywhere. So let's just say it's this one, x to the 4th power. And now we can generalize that. So in general, right, x to the nth power is equal to 1x times the next smaller power, x to the n minus 1 power. Does that make sense? That's the secret. And then when is the problem so small you finally have the answer immediately? It's like anything to the 0th power, right? You could be, your base case is x to the 1st power is equal to x. That would stop you, but you could go even further, I think, and I think it's better to go as far as possible. Anything to the 0th power is 1. That's a better base case, I think. So there's your recursive case, there's your base case. Now let's make it happen. All right, so I'll call this recursion.cpp. And so I have now a power function. It can take a double, but it has to be to an integer power. So it's pow double x int n. All right, so got to return a double then. It's meant to return x to the nth power. And yeah, let's just have it as an example. Here's what I want to be able to do, like see out pow of 2.0 to the 5th power or something. And that's what I'd like to be able to do. And so let's code it up. Given what we know now, we want to make this work. All right, so in our recursive case, it's this. In the base case, it's this. So we have to determine, like when somebody calls us, like, are we in the base case right now, or are we in the recursive case? It depends on the n, right, the power. If n is 0, somebody's taking something to the 0th power, the answer is always 1. That's your base case. Otherwise, you're in the recursive case. In general, you are equal, your x to the n power is equal to x times x to the n minus 1. X to the n is equal to x plus, x times x to the n minus 1th power. Okay, and so how do we calculate that? We have to return our x times. Somehow we have to calculate x to the n minus 1th power, but it's our job to calculate powers. It's like a chicken and egg problem, but no, it works out because it's a smaller call. Right? So we can just call ourselves and assume, due to the magic of recursion, that this really will give me the result that is x to the n minus 1th power. Really, in math, it will work out as long as I build up the right answer correctly and have the correct base case. It will unwind properly. Draw a stack diagram if you need to. It will work out. Okay, that's beautiful. And so that's the answer. Looping without loops. So there's my 32. 2 to the 5th power is 32. 2, 4, 8, 16, 32. Awesome. So there's that one. Here's a fun one that I haven't showed you before. Let's do a recursive binary search. That is for sure a thing. If you think about it, when you're doing binary search, there's something that's getting smaller. It's just an idea, though, right? What's the idea that's getting smaller? You can turn it into a number. It's your search space. Your search space gets smaller. The size of the array you need to look through is getting smaller. It maybe become empty if you're done, but like that technically lets you do recursion, right? Because the search space is getting smaller. So you do have to change up the way you're doing binary search, though. You have to turn like your search space into parameters, because it's got to be calls to the function. Like you need to be able to see it getting smaller. So like low and high need to now become parameters. So you'll call it a little bit differently, but that'll do it, right? That'll turn it into recursion, binary search recursively. Watch this. This will be fun. So let's steal it this way. We'll change it up. So here's the iterative version, right? That's the way to say it. And then we'll steal the vector library, steal some calls to it. Here. So all right, we've got all this stuff. Here's how we need to eventually call it, though. We want to call it with the thing I'm looking for, and then also the starting search space. Like we're going to add low and high to the parameters. So the initial search space is from 0 to v.size minus 1. Yeah, so that's what it needs to look like. So those are going to be your initial calls. So let's call it with the search space as well. And so we had to add these here. Int low, int high, so we don't have to calculate them here. All right, so there's that. And then we have to determine, like, are we in a base case or are we in a recursive case? If you think about it long enough, the base case is like, what am I done? When do I know the answer immediately? I don't have to look in the middle of anything. Like, I don't have to deal with these low and highs. It's when the search space is empty. Does that kind of make sense? Like, when the search space is empty, I'm done. I know the answer is not there. Like, it's not there. It's -1. So first of all, we need to get rid of this loop. And it's either base case or recursive case, and we're in the recursive case. We're in the base case if the search space is empty. If low has passed high, then that's our base case. Search space is empty. I've got nothing left to do. I trust that if you thought about it long enough, you'd get there. You get to this, return -1. That's our we didn't find it. A sad face. I could have just copied it. Otherwise, we're in the recursive case. So I need to unindent all of this, and there's no more loop, so I don't need that closing curly brace. So otherwise, we're in the recursive case. We're still here. It's the recursive case. We're in a non-empty search space. So it's like our job is to binary search v for this value, and the valid places, our search space where we could find it, is between index low and index high. Okay, that's our recursion right now. So still we need to calculate the midpoint, right? Still calculate the midpoint, and based on that midpoint, we want to binary search to the left, binary search to the right. Does that kind of make sense? So it's not like in the loop we're looking to the left, but kind of the job right now is binary search to the left. Call myself. Does that kind of make sense why it becomes recursive? Like, all right, if it's anywhere, it's over here. Like, call it on myself with a smaller search space. This will find the answer. So if it's anywhere, it'll give me back the place where it lives, or -1 if it doesn't find it. It's between the same low, right? If we're looking to the left, same low, and it's the high that changes to mid -1. So I'm passing it now. I'm passing min minus 1 into the new high. Do you see that? This is a call to myself on a smaller thing. Due to the magic of recursion, I get to assume it will give me back the right answer of the index where it finds it, or -1 if it doesn't, and I just need to build up my final answer of the search between this bigger range from low to original high. Does that make a little bit of sense? I hope it does. And how do I build up the answer based on this? I just assume this gives me back the right answer, right? So my answer is this one's answer, this call's answer. So I just need to return that result. I hope that makes a little bit of sense. It's like I'm just handing off the whole thing to this problem. It will correctly, I get to assume it's going to correctly binary search in the smaller search space, and its answer is my answer. For my bigger search space, it's still my answer, right? It's like I've whittled down and figured out that it's somewhere in here. Go smaller version of me, go find it. You see that? So yeah, this opposite way is like, all right, if it's too big, binary search to the right. It's going to be, all right, return a result of me binary searching between not low to high anymore, but it's a smaller search space. Low is change, right? I want to look to the right. That's going to be mid plus 1 becomes the new low. Does that make sense? And there's a smaller call to myself. I get to assume it's going to correctly find the thing or not find the thing. And my answer is its answer. You see that? That's it. The here, when we do find it, it works like this, right? You still return mid. If you find it at that index, your answer is still like once you have the answer, return the answer. You're done. That's where it will eventually some call to the recursion will eventually get to here, like it finally found the thing, and like all these other calls will just keep on returning that answer, shoving it up, or you'll get down to the emptiness call, and like all these recursive calls will eventually just like keep on giving back the -1. But that's it. That's the recursive binary search. Does that make a little bit of sense? Yell at me, ask me questions about this, because this is a fun idea. Binary search can be recursive, because the search space is getting smaller. My answer is this smaller answer. Isn't that cool? So yeah, let's see if it works. Look at it. It does. I get 0 for 2, does begin there, and -1, there is no 1. It will correctly get to this base case and return -1. I'll just keep on giving back -1 because like it went to the left a bunch of times. Like this call is like just keeps seeing -1, keeps on returning it. So I highly encourage you to like take this to the C++ tutor website. Watch the diagrams for like the animations for how it's unwinding. Draw the stack diagram yourself as well. Very, very useful stuff. So that's recursion. Cool, huh? So yeah, those are fun examples. Let's next talk about makefiles. So what are makefiles? They're just a way of automating compilation. Remember what that means. Everybody like overrides this term and pretends that compilation means a couple things, but really, compilation is the process of taking a single CPP file, single source code file, and turning it into object code or machine code. So it's G++-C, that's the compiler part. Just compile a single file into a .o file. All right, so you can do it separately now, you know how. And then the linker, the linking stage is you take a bunch of precompiled stuff and you combine them. So you take a bunch of your .o files and you compile it with other .o files that you've already made, and like compiled versions of libraries like IOStream and like Vector, all the stuff you're using, combine them together in like one last call to G++. It'll find the linker for you, and then like make a /recursion or whatever. That creates finally a runnable program that you can do with the /. But yeah, so it's best to do separate compilation, because if you change one thing, you don't have to like rebuild everything. So this is what we should do. Let's make a recursion library using separate compilation. So like I'm going to split up recursion CPP into another file. We'll have like recursion library with these functions, pow and binary search. And then we'll have a main file that like includes the library. So let's start that. Okay. So let's see. Let's do the header file first. Recursion.h. That'll be easy. Include your header file guards, and then like here are the declarations of all those things. Pow, binary search. Just declare them, and remember you cannot use namespace standard in a header file, so you have to say standard : vector. But in the implementation file, you're good to do whatever you want. So you got to do that, and then let's get rid of that one. In the recursion.cpp is where you put the implementation, and then also let's have just like a file with the main function. I'll call it main.cpp. That's where I'll take the main function. So let's steal these guys. Oops. Steal those, put them in the main function file. Technically won't need that. And the main function will have this. There, so there's the main file. It will include our library, include recursion.h. That's how it gains access to things, and that gives it vectors as well, so that's perfect. And then the recursion.cpp file should, it actually needs it this time, doesn't it? We need to include our header file, because that's where vectors comes from, and then we can say using namespace standard in the implementation file. That's totally fine. So yeah, this will give us, we need that for including vectors, saves us time, and then yeah, we give all the implementations of our stuff. So I've split up this program quite a bit. I've got now the main.cpp file that uses the library. I've got the header that declares the library, and I've got the implementation file for the library that gives the implementations of all of the stuff. All right, so they're all working together, and we want to separately compile them. So what we want is, we want to be able to say like recursion .cpp, compile that just by itself into recursion.o. Main.cpp, because it's only the cpp files that you compile. Give those both to the compiler to create the .o files. Recursion.o, main.o. So that's the g++-c that will do that. That's the compilation stage. We want to do that separately from the linking. So do that, and then link, and then you'll make your final file called like recursion or whatever. That's what we'd like to do, because separate compilation lets you not have to recompile things. If I change the main function, I don't have to recompile recursion.o. It's already safe. I just need to relink. All right, so make files let us automate this process. All right, so there's an example make file down here, but like here's what they look like. It's a bunch of rules, right? Every rule looks like this. You got a target name, a colon, a list of ingredients or requirements, all the things you need to make this thing. Then you tap over and give a bunch of command line commands to on the terminal to take your ingredients and build your target. Okay, so yeah, that's it. That's what it looks like. And so you just make a bunch of rules for a bunch of things, like do your separate compilation with the .o files first, and then make a final rule to combine and link those .o files. All right, so that's what we're about to do. And then once you've done that, you can say make on the terminal, like this needs to be in a file called makefile with a capital M, and then you say make, give the target name, it will go and it will build this if it has the ingredients. If it doesn't have them, it will go and find those rules and make it. Isn't that fun? That's pretty cool. And if you just say make by itself, it'll run the first rule in the makefile. So yeah, read that, but let me do it for you. So kind of what we want to do is automate this process, like g++-c on main.cpp to make main.o, g++-c on recursion.cpp to make recursion.o, there it is, and then combine them, g++ to combine them on the .o files into a final thing called recursion. And so it all still works. So that's our separate compilation. Let me remove all those things, get back to a blank slate, and let's make a makefile to do that. It's got to be a file called exactly makefile, capital M. And so here, what do I want? I want a way to make main.o, right? Out of main.cpp. That's what I need. And then how do I make it? It's g++-c on the cpp file. Same for recursion.o. Do it. You need recursion.cpp to exist, and you run g++-c to compile it. And then finally, for my final executable, which I'll call recursion, I want all the .o files, main.o and recursion.o. You space separate them, and then you tab over and like, what do I need to do on the terminal to take both of these and link them together to make the final thing I care about? It's g++, give the things, -o, your target name. And that's it. All right? And usually you put the most important rule at the top, and I'll show you why. So now you can just say make recursion. Well, you can say all the names, like say make main.o, that's fine. Make recursion.o. That's fine. It'll find the rule and do it. And then make recursion for sure will work. And it will run. Isn't that beautiful? But if you don't have anything to begin with, you have no .o files, no recursion file. Like you're back to a blank slate. You just say what you want. Make recursion. It will notice that it doesn't have these things, but it finds rules to make them. And so it'll make them first, and then build what you wanted. That's perfect. And you could have just said make, because the first rule is the one that gets run if you just say make. And this will recompile stuff for you in the most efficient way possible. So if in main.cpp I add a new line, I say like, all right, binary search for something else this time. Binary search for the number 8. It's only main.cpp that needs to be recompiled into main.o. Recursion.o is safe. Nothing has changed. So I can recompile, and it will notice that. If I say make recursion, or just say make, it notices that main.o is out of date, so it recompiles that one, and links with the old recursion.o. Isn't that beautiful? That's the beauty of makefiles. It will recompile things for you in the most efficient way possible. I love that. All right, so that's those. That's makefiles in a nutshell. Yeah, I don't have too much more. Let's do bitwise stuff now. Bitwise operations. So remember that those are things that act on individual bits of numbers. It aligns the bits of individual numbers, and it does logical operations on them. Like and 0 is false, 1 is true. So like and lines up, and it produces a third number. It's like false ANDed with true is false. Anything ANDed with false anywhere is false. But if they're both 1s, then it makes a true there. And then OR is the opposite, right? It does the OR operation. Like if there's a true anywhere, it makes a true. There's both 0s. That's the only way to make a 0, right? There's that one. There's bitwise negation, which flips all the bits. There's exclusive OR that does kind of like OR, but exclusively, so that it's a 0 if they're both true. That's the one time it's also false. Or sorry, it's also false with double zeros as well. But one exclusive OR with one, it's not true exclusively. All right, so that's why it's a 0 there. It's only true if they're different. 1 versus 0 or 0, 0 and 1. That's the only time it makes a 1 down there. That's exclusive OR. And then you got your shift operations. You can shift over things to the left, bring in new things on the left. And you can also shift to the right. All right. So it's going to chop off bits from the left if you left shift, because there's like 32 bits for an int. So just keep all that stuff in mind, and let's talk about it. Yeah. So integers, for example, are 32 bits long. So you got a number. Like you got a big long number. Think about what bits are involved. There are bit numberings as well. So the rightmost bit is bit number 0, this is bit number 1, bit number 2, bit number 3, all the way to bit number 30, bit number 31 is the last one. Okay, that's the highest bit. And then your bitwise operations are going to do logical operations on the bits of usually 2 numbers except for the not. And so, for example, yeah, and or, not exclusive OR and shifting. And is good for checking bits, OR is good for setting bits, exclusive OR is good for flipping and toggling bits. All right, but you can do more than just those things. So go back to my examples, but let's have an example of, like, let's say we've got a number. This is our number in binary, and we want to know if bit number 2 is set. This is bit 0, 1, 2. Bit number 2 is set, and we'll tell that to you. What you do is you AND with a special number with just a 1 right there and a 0 everywhere else. Because that 1, or the zeros, first of all, are going to 0 out everything. And if this 1 is going to pick it out if there is a 1. If there is a 1, it'll give you a non-zero value. If it was a 0, it'll give you the whole answer is 0. That's what you're going to compare against. That's what AND is good for. Okay? Does that make sense? So that'll let you like check if a bit is set. OR is good. OR is good for doing the setting, like force a 1 in a position. So keep that in mind. What else? What else? And then, yeah, exclusive OR is good for flipping bits. It's like if you have a 0, you can just keep exclusive ORing with 1. If you have a 0, it'll make it a 1. And then if you have a 1, you exclusive OR that with 1, it'll flip it back to 0, because they're the same now. It's only true if they're different. Okay? So yeah, just remember all your stuff. Let's have some examples of, let's make a function that multiplies a number by 2 to the nth power. That's an example of a shift, right? So like you're given an x and an n. So like, let's say that the user gives you x being 3 and n being 4, so they want to multiply 3 by, your job is to calculate 3 by 2 to the 4th power. Does that make sense? Which is the same as 3 times 16, which I did the math as 48 apparently is the right answer. And the way you get there is to start with 3 and you can shift. That's another way to do it without actually multiplying. because what is 3 but 1, 1 in binary? If you shift that by just 1, that is equivalent to multiplying by 2 to the first power, isn't it? Because like it takes the 1, 1, it moves it over and brings in a 0. It makes 1, 1, 0. And that's 6 in decimal, yes? And so the same is true for like, all right, if you take 3 and you shift it by 2, that's going to then multiply by 2 squared. Because it produces, starts with 1, 1, moves it over twice, brings in 2 zeros, and that is 8, 9, 10, 11, 12. All right? That is correctly multiplying by 4. See that? And so in general, if you want it multiplied by 2 to the nth power, you're going to left shift by n. You see that? That's what I want. So yeah, here's the two things I'm going to write. So let me just write them. Oops, what did I do wrong? There we go. So here, let's put them up here at least. These are the things I want to eventually create. This will be int, and of course both of these numbers are, or both of these things, like they got some weird stuff out of the PowerPoint, so I need to replace the weird space characters with normal space characters. I think that's fine. There. Now it's happy. So let's do this one. Multiply by 2 to the nth power, so we can do something like this. See out. Multiply by 2 to the n, 3 and 4. So take 3, multiply it by 2 to the 4th power, or 16, using bitwise stuff. So you return, start with your original number, left shifted by n. That'll work. $48. Beautiful. All right, so there's that one. And then the next one I want to do is let's have a flip bit function that takes an original number and it flips a bit number that I care about flipping. So like bit number 0, flip it. Bit number 1, flip it. That will go in the which bit part. Okay? So yeah, let's say, like, for example, if you are given, let's see, how do I want to think about this? Let's say we've got, what's a good example? Let's say we've got this number, 1101, and I want to flip this bit of it, bit number 1. All right, that's bit number 1. So to do that, you can exclusive OR with a number with a 1 in just that bit position and a 0 everywhere else, because the 0 is an exclusive OR will do the preservation, and then this exclusive OR with a 1 here will flip it to a 1 if it's different, if it was already a 0. See that? That's perfect. And this is, you can keep on exclusive ordering with that to flip it from a 1 to a 0 as well. So like if it was already 1, 1, 1, 1, if you wanted to flip this bit, you would again exclusive OR with a number with just that bit set, bit number 1 set. So that's really the number 2. But you don't have to worry too much about calculating that. It's going to preserve all these guys, and now they're the same, so I get a 0. Cool. So what's the easy way to always get a number with a certain bit set? It's you start with 1, that's the number with the 0th bit set, and shift it over by what bit you care about. So I want a number with bit number 1 set. So I take a 1, I shift it over to have bit 1 only set. Does that make sense? That's the secret. So yeah, that's what this stuff is good for. So just in general, right, you've got, oops. Let's say I've got this number. Oops, go away. Too many things popping up. Let's say I've got this number, 0, I don't know, 1, 1, 1. And I want to flip this bit, bit number 2 now. All right, so I want to exclusive OR with a number with just this bit set to flip it. This will preserve everything else. The zeros will preserve all these guys. It'll bring it down to like the 0 and the 1, 1, because they're different. And these are the same, so it's still 0, so it preserves them. And then this one will be flipped to a 0 because now they're the same. See that? It's going to do the right thing. And so what do I want to exclusive OR? I want to exclusive OR with this number, 100 in binary. But how can I easily get it? Binary. You start with 1. That's a number with just the 0th bit set, and then you shift it over by 2, right? Because it brings in 2 things. It makes 100. It's always the number with that bit set that you care about. And so that will do what we want for flip bit. So what were these? This was the number 12, 13, and this all ones here was the number 15. Let's print those out. So see out flip bit. start with 13 and flip bit number 1 of it. That should make 15. And then if you flip bit number 1 of 15, it should turn it back to 13, right? Turn it on and off. That's what I want. And we've just discovered that, all right, what you do is you take your number and you exclusive OR it with a number with just that bit set that you cared about flipping. 1 shifted by 1 for bit 1, 1 shifted by 2, left shift to make the number with just bit 2 set. You don't even have to do any math. Just like, all right, 1 left shifted by which bit? Does that make sense? That'll do it. Cool. So yeah, this 13 goes to 15, 15 goes back to 13. When you flip bit 1 at least. That's pretty fun. Yeah, I think that's most of it. So study this little study guide. Write this on your test cheat sheet if you need it. But that's what it's like. That's what those do. Go back to the lecture if you need more examples. Those are bitwise operations. And then, yeah, the last real thing I want to talk about is exceptions. So exceptions are a way of alerting to somebody that an error happened and you're handing off the problem to them to handle. All right, so runtime error is a good example of an exception. It's just a type that was made in the standard except header that takes a string that describes what went wrong, and you can throw that. You can throw anything. You can throw an int, right? Throw a string if you want to, but people tend to throw things like this. And so the way that you do it, the way that exceptions work, is you have code that might throw an exception, and you wrap that in a try. All right, you wrap that in a try, stuff that might throw an exception, and then you catch all the different exceptions that may be thrown from that code. All right, so it handles it, and yeah, it'll just like when an exception occurs, it will jump out to the closest try, or if you didn't try catch the exception, it will turn into a runtime error. All right, but the whole point of exceptions is you're supposed to notice the error, and then you don't know how to handle it, so you throw it. You throw the exception. It makes no sense at all to catch the exception in the same function that noticed it, that threw it, because you could have just used an if statement. Right? Throwing is so that you give somebody else and some other function way down the line control again. That's how it works. Okay? So it's forcing somebody to go and catch it. Somebody other than you. You're not supposed to notice it and catch it because you could have just used an if statement. All right? So let's go and make an example of that. So let's see here. Yeah, so you try code that might throw an exception, and then you catch all of the exceptions that you know how. You can chain those, chain those blocks if you need to. Just keep on doing catches. And you should always catch exceptions by reference. Okay, and that's what you need to do, just for inheritance reasons, memory safety reasons. Yeah, I can talk more about that if you want, but let's have some examples. So first example, let's have a power function that throws an error when it's given a negative argument, because we did our pow example, right? Recursion, pow. This guy is not quite correct, is it? Where am I? There. Not quite correct, is it? Because if you gave something to like the negative first power, it would just keep hitting the recursive case, and it would like to the negative 2 power, negative 3 power, it would never get anywhere. It would blow up the stack. And so let's keep that from happening. Let's throw a runtime error instead. If we ever see a negative argument, let's not let it happen. Okay, that's what I want. So standard except is where that lives. And I'm gonna need a string eventually, so I'll include the string library too. But standard except is where runtime error lives, and so don't even let it try if you get a negative argument. Like, don't let the user be able to do this. Like, pow 2.5 to the 5th power is fine, but to the negative 5th power is never going to get anywhere. It's going to blow up the stack right now. So let me show that to you. Boop. So it just blows up the stack after it does the first one, right? We get a seg fault because of that. We run out of memory. And so yeah, let's have an exception get thrown instead. So here we are, we're noticing the problem. So if n is less than 0, we don't know how to deal with this in recursion land. So I'm going to throw a runtime error, and to the constructor of runtime error, you can give a string that describes what went wrong. So can't handle, or can't take a number to a negative power. And so that's the error. We're just shouting that out to the world, whoever wants to catch it. Remember that you cannot, or you could, but you should never catch an exception in the same function where you threw it. There's no use putting this in a try catch. It's completely useless. I hope you see that, right? There was no need for the try catch. Like, you noticed it here. If you know how to handle it here, do it. the whole point of exceptions is to notice the problem and have it handled far away. Okay, that's it. All right, so here, down here is where we should be handling it. In main, that's where we have more context maybe. And so if we don't catch it, at least we have a better error this time. Like we get the runtime error, it becomes an actual runtime error because we didn't catch it from here, but we could have caught it. So we can do try catch. So catch, what do we know how to catch? It's a runtime error. We catch it by reference, call it E, and now we can use it, like handle the error, maybe ask the user for another power or something like that. But I'll just be lazy and I will be like, let's output e.what. That's a method that runtime errors have that will spit back out the string that you put into it. So there, that's us handling the error. We'll let the program continue. So there it is. Can't take a number to a negative power. So you could do something real here, but that's a good example, I think. That's my first example. And then the next one is, let's have a bit flipping function that throws an exception if they're trying to flip an invalid bit, because you know that you should only be allowed for an int to flip bits 0 through 31, right? Somebody asked for a negative bit flip, bit 32 onwards for integers. Those don't exist, so you should throw an exception. The user did something wrong. They should recover somehow. All right, so let's steal now our flip bit function and make it better. I honestly don't even know like what would happen if you tried. It might just do weird stuff, undefined behavior, if you tried right now. Like 15.1 is correct. That'll turn it back to 13, but like 15 negative 1 doesn't make any sense, right? What will it do? Like I think it's just undefined behavior. It will compile. It does something really, really weird though. Not useful. So yeah, that's what I want to talk about. So yeah, let's fix it. Let's say that if somebody asks for a weird bit to be flipped, it's like which bit was outside the range from 0 to 31, so it was like either smaller than 0 or bigger than 31. If it's outside of that range, then we'll throw something. That's an invalid one now. If it hits here, let's throw a string. That's my example. Let's just throw a string. I can build a string in the constructor. This throws a C string, by the way. You can't do it like that, but you can convert it to a C++ string by putting it in the string constructor. So yeah, just remember that. This is how you got to throw a string, or you make a string variable and just throw that. But here's how you throw it in one line. I'll just say invalid bit. And so here I am throwing it, and that's much better now. So now we get an exception, but it stops the program, turns into a runtime error because I didn't handle it. All right. Again, do not try catch in the same function where you threw, because there was no use throwing. Like if you know how to handle the problem, as soon as you notice it, do it, handle it. All right. The whole point of exceptions is you can handle it far away. You jump to the handler. All right. So here, now let's catch it. We can catch a string. That's the kind of thing that might get thrown. You should always catch it by reference. And to handle it for real, maybe you ask the user to try again or something, but I'll just be lazy and output that string that we caught. And that will let the program continue and be happy. Isn't that nice? Do remember that exceptions, I don't know where I said this, but the exception throws, once an exception gets thrown, it jumps to the corresponding catch block, and then the entire try catch is over. It does not come back to the code after. It does not come back. So if I have another line, like 15.2 here, we will never get to this line. Because this line throws the exception, it will never come back. You need to come back manually if you want to. All right, maybe put this in a loop somehow. Do something. We will never get to here. See it not happening. Like the second the exception occurs, just C++ thinks all bets are off. It jumps to the catch block, handles it, and that finishes off the try catch. So you should put the rest of the code somewhere, just like have multiple try catches. Handle it somehow, but it's never coming here if we know for sure that this line is throwing an exception. All right, so you throw it where you notice the problem, and then you handle it where you have enough context to handle it outside of where you found it. All right, so yeah, that's kind of what, like, if you have a vector, for example, v.at 42, like if index 42 doesn't exist, the vector throws the exception. It has no clue what you meant. It just has no clue how to solve the problem, so it doesn't handle it. It lets you handle it by throwing an out of range exception. Okay, hopefully that's making some sense. So go back to your book, plenty of examples there. But I think that's what I wanted to say. So yeah, that's the cheat sheet. I think we talked about everything here now. Write that down if you need it for the real test. And I think that brings us to the end of the class. You made it. So there's nothing left for me to say except for good luck. Let me know if you have any questions about anything. I'd be happy to help. Come to office hours before the test. But yeah, I think that is officially all that we have for the semester. Thank you very much for putting up with me. We made it through. All right. So I'll see you later.